Alright, we're on the last example for these volumes of rotation. Sure has taken long enough for us to get through it, but we're almost there, guys. Thank you for hanging in there. Alright, let's start with just looking at what kind of shape we have. We got a couple of things going on here. These are two curves. So it's going to be a little bit different, a little bit harder to see it, but it's really not going to be that bad as long as we keep track of which one's on top or bottom, outside, inside, that, and so on. So let's start with the first curve, y equals x squared. That's going to be down here. And then we're also looking at the curve. Let's go ahead and take that back actually. It's going to be y equals x squared. The curve y equals the cubed root of x, which is going to have a curve going the opposite direction. Now when I look at this, notice that there's no other boundaries, but these two curves do make a bounded region. It's in here. What we need to try and realize is where does that bounded region meet on the x and the y axis? Well, it's at 1 and 1 because these equal each other at 0 down here and at 1. So that helps us a little bit, something to keep in mind as we were saying this, that this bottom one is x squared and this top one is the cubed root of x. So let's go ahead and ask ourselves how we're going to piece this together. Is it attached to the axis of rotation? The first question is the x-axis. No, it's not. We have some empty space down here on the bottom. So that means that our volume is going to be the difference of the radii. So volume equals pi times big R squared minus little r squared. And which direction are we going in? Well, if we're rotating around the x-axis, that means that we're traveling horizontally. So it's going to be dx, and our boundaries are in terms of x. Thankfully, we could see easily where these two equations intersected. So we're going from x equals 0 to 1 on the x-axis. And it's actually going to be the same thing on the y-axis. Let's go ahead and see what else we can do with that. We need to figure out what the big R and little r come out to be. So the big R is from this outer edge all the way to the bottom. This piece that I'm coloring in here. So that outer edge to the bottom is going to be that upper curve, which is cubed root of x minus 0, or just cubed root of x. For the inner radius, which is from that bottom boundary to that axis of rotation, that little r is going to be x squared, top minus bottom. The bottom is the axis of rotation, which is 0. That would simplify to just x squared. So our big R is cubed root of x. Our little r is x squared. And the volume is going to equal pi times the integral from 0 to 1 of cubed root of x quantity squared minus the little r, which is x squared and dx. Let's take a look at b and see how it changes. The main change here is that we're going around the other axis. So let's go ahead and get our curves drawn so we can see what we are dealing with. We know that we still have the cubed root of x, and we also have the square root of x, or x squared, underneath it. These aren't completely accurately drawn. In fact, this cubed root of x would rise a little bit higher before growing out to the right. But it's okay for just this quick sketch that we're looking at. We notice that we still hit the x and y axis at 1 and 1. It's going to be helpful as we try to rotate around. Since we're rotating around the y-axis this time, we are going to again have some of this empty space here. So that means that our volume is going to be pi times the integral of big R squared minus little r squared. Now we're traveling in the y direction. Since we're rotating around the y-axis, it's going to be dy. And fortunate enough for us, our limits of integration are still the same, from y equals 0 to y equals 1. So let's figure out what that big R and little r come out to be. Well, the big R Starts from that axis of rotation all the way to the outer edge. Well, this curve here is y equals x squared, but another way of thinking of that is x equals square root of y. So big R is going to be square root of y minus 0, or just square root of y. Now for this other curve, it's going to be a little bit different. It was the cubed root of x, and when we change that into terms of y, that's going to wind up being, it's like x to the 1/3 equals y. Well, how do we get it to be the other way around? It would be x equals y to the 2/3. Oh, pardon me, not y to the 2/3, y cubed. X equals y cubed. So for little r, on the inside, we're going from that curve to the axis of rotation. That's going to be r equals y cubed minus 0, or just y cubed. So little r is y cubed, big R is the square root of y. And to put these together, we have the integral from 0 to 1. We got the constant pi on the outside. Big R is going to be square root of y quantity squared. And then the other one is going to be minus little r is y cubed squared dy. Let's look at part C and wrap this up. Now we're going to rotate around the line y equals 1. So let's start out with our x and y axis, see what our picture looks like, and start asking ourselves the detailed questions that help us determine how to set it up. So we still have the same kind of shape, almost like a flower petal here. Still have that same blue shaded area on the inside. But now we're going to be rotating around this line y equals 1, which is here. So ask yourself those same questions. Are we attached? No, we have some orange empty space here. We're not attached to this axis of rotation. We have some empty space. So that means our volume is going to be the integral of big R squared minus little r squared. And we still have those same convenient boundaries from 0 to 1. It doesn't really matter if it's in the x direction or the y direction, but let's clarify for ourselves. If we're traveling, if we're making disks around this axis, then that means that we're traveling horizontally from 0 to 1. So that means this should be a dx. That also means that our functions should be in terms of x, or y equals some function of x. So let's start with the big radius. It's going to start at the axis of rotation and build itself all the way down to this bottom curve, and that bottom curve was y equals x squared. So big R is 1 minus x squared. The little r is on the inside curve, which was the cubed root of x. So little r is going to be 1 minus the cubed root of x. And then big R over here was 1 minus x squared. So when we set up our final expression, it's going to be pi. Whoops, I almost forgot that on the very first one. Pi times the integral from 0 to 1 of 1 minus x squared quantity squared minus 1 minus cubed root of x quantity squared dy. And now we're done with example 6 and all the volumes of rotation.